Good afternoon. So we can start today's session. So it is live session on week 12 videos. So recap is there are conditional mean as estimators, then linear estimators are there, then about Wiener filter, then about super resolution. These topics were discussed in week 12. First one is stochastic estimator, mean square estimation. So we want to so in the case of a blurred image, you know F is a blurred image, G is a clean image, then H is a kernel, blur kernel. This thing you know, right? But normally it won't be like a nonlinear function, no. So how to find this clean image F from the blurred image? So the function that we want to find out is f, so that we want to estimate. So if the random variable is a constant, if we know that it is a constant, then the mean square error is given by like this, no. So the original random variable is y, that we want to estimate, but we know that it is a constant. So what constant we are estimating? So its error is like this. So this error we want to minimize. So this can be written like this. So if you are taking the partial derivative and if you are equating to 0, then we will get it as expectation of y. Okay. So coming to our case, that is nonlinear mean square estimate. So we know that the estimate of y that we want to estimate is not a constant but a function of x. Say a function of a clean image G, function of a blurred image, the clean image we want to estimate is a function of a blurred image G. Okay, so it is a function of x. So c of x is what we want to find out. Then we will write the error as expectation of y minus c of x the whole square. Then if we find the derivative and equate to 0, we will get it as that function we want to find is equal to expectation of y given x, that is conditional mean of y given x. Okay, so which is the conditional expectation of y given x. So given x, given a blurred image, if you are finding the expectation of y, then that expectation of y given x will be our estimate of x. Okay, sorry, y is the blurred image. So given a condition of what a sharp image x, want to find out conditional expectation of y given x, then that will give the estimate of y. Okay, then the special case of nonlinear estimators is linear mean square estimator. Here we are taking the case of linear estimator, not a function of x but sum of weighted values of x. So in that case the solution for AI can be written like this. So we want to find the estimate of y, right? So we want to find out AIs. So how we can find AI is R inverse R, where R is a square matrix of elements like this and small r is a column matrix. Then comes normality theorem. I think my connection from tab is low, so can't write anything. So for normality theorem, it states that if y and xi are jointly normal with 0 mean, then the linear estimators of y are identical. So this theorem tells the equality between linear and non-linear estimators. So that is, a linear estimator, a non-linear estimator can be equated to a linear estimator if the random variables y and xi's are jointly normal with 0 mean. So this theorem is helpful for other cases also. Then we dealt with Wiener filter. So in the case of Wiener filter equation can be derived like this. So we have a blurred image G. So blurred image is with you, G. You have to find out the original image F. Then the best minimum mean square error estimator of F, that is the original image, will be the conditional expectation of that original image given the blurred image. So this equation we know, right? Then using the normality theorem, we equate a nonlinear estimator to linear estimator. Then the blurred image, the original image can be written as a function of G. Okay. Then by writing like this, then using orthogonality principle, the error will be orthogonal to G, no? So expectation of f minus f cap dot G transpose equal to 0. Then after substituting the relation between f and G here, we'll get some h cap. So h cap can be derived like this. So these equations are all derived in the class. Then so this is the Wiener filter in spatial domain. Then in frequency domain also we can take the Fourier transform of this equation to get like this, where G is the blurred image and H is the blurring kernel. Then so this equation can be used in the new assignment. Then comes image super resolution. So in the image super resolution, we have a high resolution image F. In the case of deblurring, we have a clean image F, but in super resolution, we have a high resolution image F, which is passed to a degradation function to get a low resolution image G. So we have a low resolution image G. In deblurring case, we have a blurred image G. Here we have high resolution image F. In deblurring case, we have a clean image F. Okay, so in both the cases we have to find out F. So here F we can find out. So in super resolution problem, we have a high resolution image X, which undergoes a degradation to get a low resolution image Y. So Y can be written as D into X. So D can be considered as a downsampler plus average. So if we average 4 pixels, 4 neighboring pixels, and we'll give to 1 pixel, then if the input resolution is n by n, then if you are averaging 4 neighboring pixels and the output will be given to 1 pixel only, then we'll get a resolution output resolution of n by 2 by n by 2. So if we have this low resolution image n by 2 by n by 2, there can be multiple solutions. So different 4 pixels can be found out now. So because if you have a value 10, that 10 can be represented as an average of different 4 pixels. So such 4 pixels we can write anything, no? So there can be infinite solutions. So what should we do? So instead of using only one HR and one SR image, we can use multiple high resolution and low resolution images to solve the equation. So like that we will get one solution for D. Okay. Then this is the lab assignment 12. Here we have to implement Wiener filter. So you are given sigma for blur and sigma for noise. So you are given an input image lena.png. Then you have to blur the image, lena image, by using these sigmas. So you have a blurred image with you. and you have to find out the h value for every sigmas given. Then here this term can be taken as k. So for every k you have to find out. So in 3 cases you have to vary k from 0.01 to 2, and you have to find out which k performs well. So performs well means you have to find out the minimum RMS error between the original image and the estimated image. So that error should be minimum. So this is the lab assignment 12. So next I will go through one previous tutorial that was given in the NPTEL site. So the first question is, this type of questions are already discussed in the live sessions. So once again I will go through it. So for 3-bit image I, between class variance for all possible thresholds is found as follows. So it is given. So between class variances are given. If it is not given, if the question is only a 3-bit image I, you have to find out sigma b square. How? So there are equation, no. So for every threshold you can find out 2 classes. Then for 2 classes you can find the mean of the classes and variance of the classes. Then from that you can find out the between class variance and within class variance. Then you can find out the threshold which gives the maximum between class variance. So here this table is already given. So for threshold 3, the between class variance is 7, that is the maximum, right? So the threshold can be taken as 3. Then you can make the values which are greater than 3 as 1. Then the values which are less than 3 can be taken as zeros. So here 1 is less than 3, so it becomes 0, and the other becomes 0, this becomes 0. So you will get an output A. So the answer will be A. Then for the next question, wait, I will check whether I can connect through my tab, otherwise difficult to. So here sigma b square equal to 7, so that is a maximum value. So the corresponding threshold is 3. Then for the amplitudes, so for intensities greater than 3, you can make it as 1. For less than 3, you can make it as 0. So I is 0, 1, 1, 2, 2, 5, 5, 4, 6, 7, 6, 2, 4, 6, 5, 0. That can be converted to 0 is 0 itself. 1 is less than 3, so 0. 1 is less than 3, 0. 2, 0. 2 is again 0. 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0. The answer is A. And next question is, find the correct matches between images and histograms pairs given below. So the first, so which one is a higher contrast image? So histogram tells x-axis is intensities and y-axis is how many pixels are having that intensity. So the first image is a dark image, so it tells that the intensities are almost dark. So almost all the pixels are having lesser intensity. So intensity is like this, 0 to 255 will be here. So in the intensities are very dark. So this is the first image histogram. The second image is actually, we can take the third image. The third image C is very bright, no? So its intensity will be concentrated on 255 range, right side. Okay. So this is for C, this is for A. Then for the D image is having very high contrast. That means it has white color as well as black color. So its histogram will be uniformly distributed all over 0 to 255. Then the second one B has lesser contrast because it has no white color, no dark color also. So its histogram is contained in between the two ranges, 0 and 255. So lesser number of gray levels will be there in the image B. So we can match. So dark image histogram is A to Z, then low contrast image to D, then bright image corresponds to this one, then high contrast image histogram will be uniformly distributed. That is meant by histogram equalization. No, that is already covered. Then the third question, for the histogram given below, what would be the appropriate value of K for the image to be clustered using K-means clustering? So we know that so if an image is having this type of histogram, so their intensities are concentrated on these intensities, again these intensities, again these intensities. So if you are taking a three values, no three values, so that image can be clustered into 3 clusters. So that will be the optimum value of K. So K can be taken as 3. Next question is, what will be the input reference histogram if you want to perform histogram equalization first, then binary thresholding on a grayscale? Okay. So first, so image size is 64 by 64. So what is the value of 64 by 64? I'll find out. So it is 4096. Okay. So these many pixels are there. Then the intensity range is actually for the final exam, so I am not sure, but I think the similar type of question will be there. Is there any any instruction like it is an objective or descriptive? Is there any instructions like that? Okay, I think so these the question will be mostly like this. So if you are okay to on 21st, no, actually I am not sure about that. For the NSEM it is live, no, so you have to come here, I think. Okay. So the question pattern I am not sure. I think it is mostly based on this type of questions only, but some advanced questions can also be there. I don't know whether it is descriptive or objective. question bank is actually not available. If you are going through means if your basics are okay, then I think you can easily cover questions. So some questions will be of this type, I'm sure, but I don't know what type of question will exactly be asked. And you submitted all the assignments? Okay, so did you get how much mark you got for assignments? Okay. So we can go through this question. Question 4. So the intensity range is from 0 to 255. So you have 256 intensity values. Okay, but you have 4096 pixels. So and every pixel, every intensity value should be covered by same number of pixels. That is what is meant by histogram equalization. Histogram equalization means histogram should be uniform. That means if we have 256 values here and each line indicates how many pixels will have this intensity value. So total number of pixels will be 4096. So in each height should be 4096 divided by 256, that is 16. So for histogram equalization, h of n will be 16 for 0 to 255. Then for histogram modification, we should get a histogram like binary thresholding. Thresholding on grayscale image of size 64 by 64, same question, in the intensity range 0 to 255. So binary thresholding should come, where in every option we have h of 0 and h of 255 we have. So these two on these two values we should have two peaks like this. Okay, so this should be the histogram of histogram, the second histogram. So what should be the value of this blue line? If we are adding this value and this value, we should get 4096. So each line should be 2048. So the answer is D. So this is how this answer comes. Next question, question 5 is, if K-means algorithm is converged to a particular centroid and respective clusters, we can be sure that it is the optimal results. The answer is false, because it depends on what value we are taking for the value k. So that is up to us now. So if the number of clusters are actually 4, and if you are taking the input cluster as 8, then we will be converged to 8 clusters, but that may not be optimal. So it depends on how many cluster centroids we are taking initially. So it is false. Then while performing mean filtering, choose the correct statement. So increasing mask size reduces image signal to noise ratio. Increasing mask size increases image to signal to noise ratio. There is no such relation between mask size and image SNR. Mean filtering doesn't affect noise. So mean filtering is actually used for noise reduction. So if we are increasing mask size, noise will be very much reduced, no, but blurring will happen, but signal to noise ratio will be increased. So the answer is B. The next question is, solve Ax is equal to B for the given matrices A and B. I think this type of question may come, this solving and all. So A will be given and B will be given, and how what type of x you will get. So the question is, from the solution obtained, choose the true statement from the option. So so we can first find rank of A. So the equation is Ax equal to B, no? First we have to find out whether x has a solution or not. Okay, whether this type of equation we can write. Okay, so first we have to check whether x has a, so this equation has a solution. So for that, first find rank of A. Rank of A 1, 2, 2 minus 1, 3, 1. How will find out? So its rank is 2. Then rank of, next find rank of AB. That is rank of 1, 2, 2 minus 1, 3, 1, minus 2, 3, 2. So I think finding rank is okay, no? So this can be reduced to some matrix 1, 2, minus 2, 0, minus 5, 7, 0, 0, 1. So we can say that its rank is 3. So its rank of A is 2 and rank of AB is 3. Then we can say that x doesn't exist. There is no solution of x such that Ax can be written as B. So no solution. So we have to go to what type of solution? Least square solution, no? Last class it was discussed. So we have to go through least square solution. So for least square solution we know the equation, no? A transpose, so x cap should be what? A transpose A the whole inverse A transpose B. So this type of solution is available. So this is unique, but it is not the exact solution. So the answer is, solution is unique but not exact. So answer is B. And if x is exact, if you are getting the rank of A and rank of AB same, then we can say that x is exact. But there can be multiple solutions also, no? So because if you are getting rank of A as 2 and rank of AB as 2, but it is not number of rows, no? It is not equal to number of rows. So there can be more than one solution. In that case, we have to go through minimum solution. So we have a number of solutions. From those solutions, we have to get one solution which has minimum norm. No. So but here it is unique, least square solution, but not exact. Okay. So the question 8, find expectation of y given. This type of question can also come in the exam. So you are given joint probability distribution. What f of x comma y is given as x, and x and range of x and y are also given. Then you have to find out expectation of y given x. So this equation you should know. So expectation of y given x is y, then f y given x dy. So this equation is given, not given, we have to find out. So this conditional means the joint probability distribution is given. So you have to divide it by f of x. F of x can be found out from integrating this equation. So this is x square, so you will get 1 by x, then 1 by x should be substituted here. So you will get x by 2. So expectation of y given x is x by 2. So that is the conditional mean. The answer is A. Next question is very tricky question. Choose a true statement from the given set of statements A, B, C. You have to remember that the first equation itself is wrong. Like in the denominator you should have Sn by S, not Sf by Sn. So you should be careful for this type of questions. Then the second option is Wiener filter will act as an inverse filter. So but the thing is opposite. Then the third option is when there is no blur, Wiener filter will be acting as a low pass filter. That is correct. So the answer is only 3. And the next question is a blurring degradation model is given. Then you have intensity at locations are also given. So you have some correspondence between the input intensities and output intensities. No. So you have this 3 by 3 kernel. Not 3 by 3, it is 5 by 5. So its relation is given like the center pixel is multiplied by 1, then this thing is multiplied by -2, -2 is 1. So something like that is given, no? So and so the question is from the expression for the inverse filter determine if there are specific frequencies that cannot be restored. So so h of kl you can find out frequency response of h can be written like this: double summation h of mn e raised to minus j 2 pi by n mk plus nl. Here different value 1 minus, you have 1 minus to 1 only. For what type of values? For m equal to 0, n equal to 1 and n equal to 2. So for only 3 values you have values. One is at 0 0, next is 0 1, next is 0 2. So substitute here. So you will have 3 terms like this: 1 minus 2 and 1. Then you take one constant outside, common factor outside, then you will get like this, you will get like this. Then this is h of kl. So the inverse filter will be 1 by h of kl. So 1 by h of kl can be written like this: 1 by 2 l minus 1. So in order to avoid this infinity term, cos 2 pi by n l should not be equal to 1. So this term should not be equal to 0. So that occurs when 2 pi by n l equal to a pi. So that is the answer. So this is all about this today's session. If you have any doubt you can ask, otherwise it is the last interactive live session. Okay, then thank you. All the best for the exam. Thank you.